So what we get to do now that we've learned how to draw the Lewis symbols is we're going to see if we can figure out how to use those Lewis symbols to help us combine elements into compounds. We're going to look at a special type of compound to start with called an ionic compound. And just so you can kind of help keep this straight, this is going to be metals, metal, so something on the left-hand side of the periodic table, plus a non-metal, something from the right-hand side of the periodic table. So let's look at some of the specifics for this. So this is a very, very common reaction that people love to demonstrate or love to show pictures of to represent an ionic compound and how an ionic compound is formed. What we do on this one is we start with this silvery gray metal over here. This is sodium. So sodium by itself is a soft gray metal. You can cut it with a knife. Now, if you notice, they're wearing gloves when handling this. Sodium is very, very corrosive. It's very, very reactive. In case if you put sodium in a beaker full of water, it's actually going to burst into flames. You know, I used to do that particular demonstration in class, and then I caught someone's paper on fire. So we'll just look at the picture of this one. It looks pretty cool. If you take Chem 2, we'll get the sodium out. Now, sodium likes to actually oxidize as soon as it's cut. So it goes from this really, really pretty silvery gray to looking kind of dull because the air is reacting with it. When you store sodium, you actually keep it underneath oil because just air will start reacting with it. Now, over on the right, we have this little volumetric flask. You can see that there's this real pale yellowish colored gas inside. That is chlorine. Chlorine gas. Now, chlorine gas is a pale green gas. It's actually poisonous. It was used as a war gas during World War I, just a little bit. This is very, very irritating to people. Yeah. So what happens when you take this sodium, this soft gray metal, and this chlorine, this pale yellow gas, and you combine them together? Well, and combine them together, you get this great big reaction that's going to take place, and then you have something that you're going to enjoy with your meal. You have sodium chloride, NaCl. You have good old table salt. Well, how in the world did these two react? When looking to see how sodium chloride is formed, this one works really, really great to look at our Lewis symbols. So what we're going to do is we're going to start with sodium. So sodium is in group 1A, it gets 1 dot. Chlorine, well, it's in group 7A, 1, 2, 3, 4, 5, 6, 7, it gets 7 dots. Now, as we're talking about the number of dots of each of these, I want you to keep in mind that all of these elements, they want a complete set. They want to follow that octet rule. They want to become like a noble gas. So I'm going to write down a noble gas just so we can compare it to. So let's say we look at neon. Neon has 1, 2, 3, 4, 5, 6, 7, 8. A complete set, 8 valence electrons. Oh, all right. Don't tell on me, but I'm gonna give you a little secret. So I was at a conference one time and they were talking about the 3 S's of the periodic table. The first S of the periodic table is group 8A, those noble gases. I have another name, a common name for them. Now, we talked about how these noble gases, because they have a filled octet, my little electron doesn't want to show all the way at the bottom there, they don't like to react with other elements. We're going to call them the snobs. Just like a snob in school, they don't want to react with anyone. So group 8A, the noble gases, are the snobs. Now we have sodium over here. Sodium has 1 valence electron. Now sodium wants to be like a noble gas. Would it be easier for sodium to lose that 1 valence electron or to gain 7 more? Well, it should be a lot easier to lose 1 than gain 7. So sodium, all of your group 1 elements, are the sluts. They like to give it away. Oh, yeah, I did say it. Oh, I'm so rotten. Don't repeat that, by the way. So sodium likes to give away its electron. Chlorine over here, it has 7. Now I was told they 7A are the studs because they like to get electrons however they can. They can gain them or share them or whatever the case might be. Now sodium is going to donate an electron to chlorine. When it does this, sodium has given away that electron. Sodium now has a positive 1 charge. It's become a cation. Chlorine now has 8 valence electrons. It has a negative charge because it gained something that was negative. It gained an electron. Now, because sodium is positive and chlorine is negative, they're attracted to one another. They form NaCl. Now, the name that we give this, the first part we just name like it's given, we just call it sodium. The second part, we're going to change the ending to "ide." This is sodium chloride. Oh, you know, we just did a ton of stuff in just 60 seconds. We looked to see what charge they would get. We looked to see what ratio they react in, and we also looked at the name. We need to do another one of these. Let's say we take calcium. Now calcium, it has 2 valence electrons because it's in group 2A. We're going to take that calcium and we're going to react it with, let's say fluorine. Now fluorine is in group 7A. It has 7 valence electrons. So calcium is easier to lose 2 than gain 7. Calcium is going to donate an electron. Now to show that movement of the electron, I do a single-headed arrow because it's giving away the electron. It doesn't want it anymore. Calcium is not yet happy. Calcium's given away 1 electron, but it has another one to give away. Fluorine had 7 valence electrons. It's gained 1. Fluorine is very, very happy. But calcium, we've got to make it happy too. So calcium has got to find another fluorine. Now as we do this part, we're only going to be looking at 2 elements. That's it. You can have multiple atoms of each, but just 2 elements. Calcium is going to give away that electron. Now calcium lost 2 electrons. So calcium gets a positive 2 charge. Fluorine gained 1. Now I had 2 fluorines. They each gained 1, but each fluorine only gained 1 electron. So it gets a negative 1 charge. So those are your charges. How many electrons did it give away, which causes a positive charge, or gain, which gives a negative charge? The ratio in which they react. Well, for every 1 calcium, I had 2 fluorines, CaF2. What you'll find is that you can take the numerical part of the charge and flip them, put them on the other element. That comes with time. If you need to, just stick with drawing the little electron dots. That part always works. So we have CaF2, that's the compound that they form. When we look at the name, you write down the first element, calcium. And then the second element, we change the ending to "ide." Calcium fluoride. Calcium fluoride. So we looked at a couple of examples where we were making ionic compounds, metal and non-metal. Something from the left plus something from the right. Sorry, in my office, I have a bell that rings twice an hour. It's kind of crazy. All right, so ionic compounds. Ionic compounds are compounds composed of ions. Ions mean that we gained or lost electrons. A cation is positive. It's positive because it lost electrons. These are going to be your metals. The anions are negative. So if you look at how it's spelled, A-N-I-O-N. N stands for negative ion because we gained electrons, and this is going to be our nonmetals. To name them, we changed the ending to "ide" of the second element. Down on the bottom, it shows the example of sodium chloride. I drew that out on the last slide for you. This one actually starts off by looking at the electron configurations first. Notice how big and bulky that is compared to just showing the Lewis symbols. I like the Lewis symbols, so you'll see me use those a lot. Let's try another example. All right, so we're going to try 2 more examples on this slide. These are things, practice them, keep trying them. If you have any questions, let me know. Because this part, I try to show it in a very simplistic manner, but it will help you later on. What we're going to do here is we're going to take lithium and we're going to take oxygen and we're going to combine those together. So I'm going to start by drawing the Lewis symbol. Lithium is in group 1A, it has 1 dot. Oxygen, group 6A, has 1, 2, 3, 4, 5, 6 dots. Now lithium wants to give away that electron because it can either give away 1 or gain 7. So it's going to give away its electron to oxygen. So it's going to go right here. Now lithium is happy. It gave away its oxygen. It's happy as can be. Now oxygen though, oxygen has 6 valence electrons, but it wants 2 more to get to 8. So oxygen is not quite happy. It's gained 1 electron, but it wants 1 more. So oxygen is going to go find another lithium. And that lithium is going to donate another electron. Now each of your lithiums lost 1 electron. So I had 2 lithium atoms that each lost 1 electron. The oxygen gained 2, so it has a negative 2 charge. Now notice when I said a negative 2 charge, I actually wrote the numerical part first. It gained 2 electrons, and then I wrote the charge of negative. If you do it the other way, if you actually put negative 2, I wouldn't get on to you. This is just the more technically correct way to do it, and there's reasoning for that once we get to redox later on. Alright, so this is predicting the charges. Now when we predict the compound that forms, well, we had 2 lithium atoms, so we had 2 lithiums, and we had 1 oxygen. Now you don't have to write the 1 oxygen, that one is understood to be there. So we have line 2. Now on this part, the numbers are going to be written as subscripts to indicate the number of atoms of each element that combines to form a compound. For the name, we have lithium oxide. So we change the ending to ide. You don't have to tell me how many lithiums you use because I know that by looking at the charges. That's the only combination that these 2 particular elements can have because we are gaining and losing electrons. Let's try one more example. I'm going to make this one tricky. Let's do magnesium and nitrogen. Sure, why not? Magnesium has 2 valence electrons. Nitrogen has 5. Magnesium gives away an electron. Not quite happy yet. Nitrogen's not quite happy yet, so magnesium is going to donate a second electron. Now magnesium is happy and gave away both of its electrons. It has a positive 2 charge. But nitrogen 1 and 3. So nitrogen wants another electron. So what's nitrogen going to do? It's going to go find another magnesium. So let me write magnesium over here, give it 2 electrons. And this magnesium is going to donate one of its electrons. Oh, nitrogen's happy now. Now, nitrogen's happy, but when I look at magnesium, magnesium still has an electron it wants to get rid of. So that magnesium has got to go find, oh yeah, another nitrogen. Nitrogen has 5 there. Alright, so magnesium is going to give away its electron to nitrogen. Magnesium is happy, but oh no, nitrogen sodium's going to give away an electron. Oh, neither one is satisfied. We go back to magnesium. It's going to donate its second electron, and nitrogen is now happy. Yay, they're both so excited. We have filled everyone's octet or lost all the electrons that they have. It's kind of crazy. Now, each of those magnesiums had 2 electrons, meaning each of those magnesiums gets a positive 2 charge. The nitrogens each gained 3 electrons. They have a negative 3 charge. Think about it, they had 5. They want 3 more. It's a negative 3. If we look at the ratio in which they react, well, I had 1, 2, 3 magnesiums that reacted with 2 nitrogens, Mg3 and 2. That is the chemical formula. That's the part you want to make sure you know how to do. When we look at the name of it, Mg stands for magnesium, and then the second element, we change the ending with nitrogen, becomes nitride, magnesium nitride. Now, this slide looks at that sodium chloride again. I know, way back when we had Na plus Cl, and we showed how they reacted with one another. Shows sodium starts out as a soft gray metal, but down at the bottom, this particular book, one reason I really like it is it allows you to visualize. So it says, you know what, this is what sodium looks like. The atoms are packed together very, very tightly. So that is indicating that you have a solid piece of sodium, because the atoms are very, very close to one another. They're packed in just as tight as they can be. Now, that chlorine, remember, it's a gas, chlorine gas. So each of these circles indicates 1 atom of chlorine, but if you look at this is actually 2 atoms together. So we would write that Cl2. So chlorine does something really crazy. It's said to be a diatomic element. I did not take that diatomic scenario into effect when I was writing the different elements and just showing you the basics. We'll talk about that diatomic part later on. And then we add them together, and oh, a big reaction takes place, and we end up with table salt. Now, table salt, look at the structure of this. It's a solid. It's very, very symmetrical to one another. It's very, very orderly, but notice it's not quite as closely packed. The big green circles, those are your chlorines. The little bitty purple ones, those are your sodiums. And for every 1 sodium, there's 1 chlorine. They're attracted to one another because one's positive and one's negative. But if I was to choose any atom, let's say this little sodium right here in the center, it's got a positive charge. It's attracted to any negative charge that's by it. Each of the chlorines, they're attracted to all the positive charges that are right beside them. But because of the charges that we looked at, we know it's always going to be in a 1-to-1 ratio. For every 1 sodium, there's 1 chlorine. That can do some kind of interesting things right there. It took me a while to kind of get that concept that everything is attracted to one another. So as you are looking at forming these different compounds, just know that it's not just 1 sodium and 1 chlorine that are going to react. That's the ratio in which they react. I like to show these structures as being great big magnetic structures instead of if you have ever played with the little magnetics, which are these little bitty magnets, and they're in rod shapes and have little balls, and they all attract to one another. That's what's happening here. We have a great big lattice that's going to form of all these positive and negative charges. And because of that, it has some really unique characteristics for ionic compounds that we're going to see. So let's keep going. I went ahead and I included this particular slide. It talks about how you can predict the formula based on the valence electrons. So what I always recommend to my students is start by drawing the Lewis structure. Start by drawing those Lewis symbols, and then show how the electrons move from one to another, because it's a little easier. It's a little more visual, and it's easier to grasp. You will get to the point you don't have to draw them. You will look to say, oh, magnesium, it's in group 2A, it likes to get a positive 2 charge. How's that going to react with oxygen? Oxygen's in group 6A, it likes to have 2 electrons added. It's a 1-to-1 ratio. You will get to the point you can do that mentally. And that's what this particular slide is looking at, doing it mathematically, to where you can figure out the number of atoms times or multiplied by the valence charge. And so you get this overall like net charge, and you want your positives and negatives to balance. I don't like to explain it this way so much, but it's in the book if you would like to go back and refer to it. All right, time for a little question. Aluminum oxide will be written as, oh, look how tricky I am. I just gave you the name. I didn't tell you what elements it was. Well, I know you guys know that aluminum is Al. Well, it's not letting me write on the slide. Excellent. Aluminum is just Al, and oxide is oxygen. It's just O. Take a minute. Write them out. Aluminum has 3 valence electrons, and this has 3 valence electrons as a positive charge. Oxygen